Hello students, in this video we'll begin our discussion of how we integrate a complex valued function along a curve parameterizing the complex plane. So let's be given a complex valued function f. Let's just say that maps omega into the complex plane. I'm not going to assume anything about this yet, like homomorphicity or continuity just yet. Let's just say I give a complex valued function and a parameterized complex curve and a parameterized complex curve. By. Now, C is going to be a curve. It's going to be a curve in the complex plane, right? So I'm going to write like this. Z of t is equal to u of t plus I v of t, where t goes between 0, or between a and b, for example. A less than or equal to b, less than or equal to t. And I'm going to assume this function z that u and v are smooth functions, right? Where u and v are smooth functions. U and v smooth. Okay. In other words, and at least initially, I'm not going to make any sort of big deal about rectifiability of a curve, right? So in other words, in principle, you could say like, you can take a fractal curve like the von Koch snowflake or something like this, or the Cantor's double staircase where they're not differentiable anywhere, right? And of course, I'd like to do a derivative of z, right? So if z is smooth, if u and v are smooth, then I can write uv smooth implies that z prime of t, which would be u prime of t plus I v prime of t exists, right? Okay. If u and v were not differentiable or nowhere differentiable, right? Like for example, another sample path of Brownian motion, not differentiable anywhere, then we know that I couldn't do this procedure, right? And then I need to come up with some idea of rectifiability, right? But then you say, well, wait a minute, a trajectory of Brownian motion is not rectifiable. And I agree to that. It's not rectifiable. It's up to its Hausdorff dimension is a half, right? So we have to get to those videos eventually, right? But its Hausdorff dimension is a half, so I can't even compute some notion of length, right? Infinite length. It's infinite first variation, right? Impossible to do this thing over here, right? So I don't want to deal with those issues right now because complex analysis is all about smoothness and regularity, right? So we're going to assume that u and v are smooth. And of course you might say, well, how do you define the derivative at b, right? If it's closed at b, I'll do the limit from the left for the derivative b, and I'll do the derivative limit from the right, the difference quotient limit from the right for a, right? And that takes care of all these issues, right? Now let me assume that f is just continuous, right, everywhere, right? So I can make sense of this. Then we define what? Define the integral over c of f of z dz. What will this thing be? This is going to be, as we did in Calc 3, it's going to be the integral from a to b of what? Of f of z of t, z prime of t, dt. That's it. Easy enough, right? And we know what z prime of t is, we know f of z. So we're going to cross multiply these things, and this answer will output a complex number over here. So that's the definition how we integrate over a curve. And now this smells a lot like Calc 3, right? So in Calc 3, we're able to do stuff like this very easily, right? And we're thinking of things like primitives of the function f, etc. And so that's the definition. So let me make some comments on this. We say, so here's a remark. I have to show this is actually well defined, right? Because there's many ways, as we saw in Calc 3, there's many ways to parameterize a curve, right? So proposition, this is well defined. Meaning that if I give you two different curves, z and z tilde, so in other words, what is a re-parameterization? So a re-parameterization of c is a function, a bijective function, let's just say strictly increasing. It can be decreasing as well. Phi, which maps, say I have a different interval over here. Phi is going to map what? It's going to map c, cd, not ab, but cd. Phi is going to map cd into ab. Together with a z tilde. Okay, and z tilde is going to map what? Z tilde is going to map have this backwards, but it shouldn't matter so much. It's going to map CD into C, into the curve C, right? And it's a re-parameterization if you have this. If you have Z tilde, so I need to plug in values of A and B. Z tilde of T, so if I give you a C and a D, right? That's the same thing as Z of phi of T. So let's make sure that this makes sense, right? So if I plug in something between C and D, phi maps it to A and B, and that's what Z inputs, and then Z tilde inputs the things between C and D. So this is what a re-parameterization is. And strictly increasing just allows me to what? The reason I say strictly increasing is that I want to be able to change variables, right? So my goal with this is to be able to change variables, right? You can only use the change of variable theorem when you have a non-singular Jacobian, and strictly increasing means the derivative of this function is going to be non-zero everywhere, which means I can change variables, right? So let's make sure this works actually. So if we had, so here's how would you prove this proposition over here? Well, you prove this proposition in the following way. You'd say the integral, let's do the integral from C to D of what? Of f prime, I'll say C to D of f of Z tilde prime of T, right? And then what? And then times, no primes though, sorry. No primes there. Z of T. Z tilde prime of T dt. I'd like to show that this is exactly the same thing as this, right? I want to show that those two expressions are the same. In other words, I give you a different parameterization of the curve, and I get the same answer over here. But what is this thing over here? So is that true? Let's find out. So what is Z tilde? This is the integral from C to D, C to D, of f of Z of phi of T. And then Z prime is going to be Z prime phi of T times phi prime of T by the chain rule dt, right? And now, of course, I'm going to change the variables over here. I'm going to let this thing over here be my what? I'm going to let the phi of T over here be my, let's call that tau. So phi of T is going to be equal to tau. Phi of T is equal to tau. And so tau is equal to phi of T. And therefore, what's d tau? Then d tau is going to be phi prime of T dt. Good. And so now what? And so now, what does this integral over here becomes? This becomes what? Well, when T is equal to C, when T is equal to C, what does that tell you? That phi is going to map to, is strictly increasing is map to A. And when T is equal to D, the tau is going to be equal to B, right? Because you're strictly increasing, and it goes continuously up from A to B. Excellent. Then I have f of Z of tau, because phi of T is tau. Then I have Z prime of tau, and then phi prime of T dt is d tau. But that's just a dummy variable for this. So indeed, it's consistent, right? So I have a consistent way of defining these integrals over here. That's the first thing. So it's consistent. And so now what are two other sort of fundamental properties of these things? Of course, one sort of remark is that if this function, we don't want to have to think about this too carefully, but if this curve was not smooth, if there were like jumps, if there was sort of like breaking points where it wasn't differentiable, you can just avoid a finite number of breaks, and you can say piecewise smooth as if there's a finite number of like cusp discontinuities, which you can avoid by just saying the integral doesn't care about a finite number of points, right? The integrals could care less about those things. Okay, good. Or sets of measures here if you want to be very pedantic about it. Good. All right, so now that tells me how to do these so-called line integrals, or these complex valued integrals over a curve, right? And so maybe let's do an example and do some properties, right? So what are the basic properties? The basic properties are what you expect. So what are properties of these things? The integral over C of f of Z dz is the same thing as negative the integral over the opposite orientation, right? So if you just re-parameterize this curve by doing what? If you look at, like, for example, the opposite orientation is going to be a Z of B minus A minus T, right? So now if you plug in T equals B, plus A, of course, right? If you plug in T equals A to this, you're at B, and if you plug in T equals B to this, you're at A, so it flips it. So this is the reverse orientation, so we can call that like, this is like Z sub negative C, right? The parameterization of the opposite curve. But that's just, it gives you a negative sign, right? F of Z of T, dz. And then what you can say is you can say that if you have the integral over a whole bunch of curves, C1 through Cn of f of Z dz, that's exactly what you expect. And this is trivial to prove. It's just going to be the sum j goes from 1 up to n, the integral over cj. So you just break up this in terms of the sum, right? F of z dz. Okay, those are the two most salient ones. And then let's prove, this one's going to come up in the proof of the Gorsaw theorem, so let me state that more formally. And sometimes in the complex analysis books they call this like the m times L inequality, but it's actually it's very crude over here, right? So proposition, and this is called like the m times L in a lot of textbooks, m times L inequality. Okay, and so what is this so-called m times L inequality? It says that if you define if length of gamma is going to be the integral, if the length of a curve, let's be more specific about this. If we define length of C by integral from A to B of the absolute value of the modulus of Z prime of T dt without the parameterization. So if that's what the length is, then what can we say? Then, and we actually know for smooth curves that we saw in real analysis that actually, undergraduate real analysis, that actually defined a length, right? In other words, if the curve was, we called that had bounded variation, right? And of course, these smooth curves on convex have bounded variation. For curves of bounded variation, this integral over here is going to converge to the length, right? That's like the arc length formula, right? This is basically just the arc length formula. Then, the absolute value of the integral over the curve, f of z dz, is the absolute value of the integral from a to b of f of z dz, f of z of t times z prime of t dt. And how can you estimate this? You can put the absolute value inside the integral. You can say this is less than or equal to the maximum over the curve c of the absolute value of f, right? So in other words, take the largest the function can be along that curve, right? The maximum modulus. And then what's left over is going to be, you can pull that out of the integral, and you just have the integral of the absolute value of z prime of t dt. So that's going to be the what? That's going to be the length of c. And so sometimes they call this m for the maximum of the function times L for the length of the curve. So in other words, if you're integrating along a curve, you find the maximum value of the function, the maximum modulus of the function along the curve. That's a fixed number. It's like the curve is a compact set, right? I have a compact set and I have a continuous function over here. I'm assuming now that f is continuous, the modulus is continuous. Continuous function over a compact set achieves the maximum. That's m. And then what's left over is going to be, I'm assuming the curve is rectifiable, so that integral represents the length of the curve, right? So in other words, the overall length of the curve times the maximum of the curve is the absolute largest in absolute value or in modulus that the integral, this curve integral of the complex value function can be. It's a trivial inequality, but it comes up a lot in making estimates using the Cauchy theorem, which we'll see in further videos. Thank you very much.